This week, scientists announced a new deep-sea expedition to investigate a discovery that challenges one of the most fundamental assumptions in biology. The mysterious phenomenon is colloquially known as dark oxygen produced without sunlight, and it's being found in the very same part of the ocean that is now being targeted for deep-sea mining. Hello, and welcome to the Ocean News Podcast, an audio series in which we take a deeper dive into the most important stories and biggest headlines from the oceanographic newsroom. I'm Eva Cahill, the Editorial Assistant here at Oceanographic, and today's episode takes us to the deepest, darkest depths of the ocean. Yesterday, 3 scientists working in partnership with the Nippon Foundation announced the next phase of a deep-sea expedition to investigate a phenomenon known as dark oxygen. The discovery challenged one of the most fundamental assumptions in biology. Dark oxygen was first discovered by the study's lead scientist, Professor Andrew Sweetman, back in 2024. Sweetman had ignored the findings that led to the discovery for the best part of a decade because it contradicted the widely accepted belief that oxygen could only be produced when sunlight was present through photosynthesis. But, while conducting experiments on the deep seabed of the Clarion-Clipperton Zone, a vast region of the Pacific Ocean, Sweetman noticed something that shouldn't have been possible. Despite the total absence of light, oxygen was being produced on the seafloor. So, how was this possible? The answer appears to lie in strange, ancient formations scattered across the deep ocean floor, polymetallic nodules. These potato-sized, rock-like lumps form at an almost unimaginable pace, growing just 1 millimetre every million years. Layers of iron and manganese hydroxides slowly accumulate around a core of ancient debris, like fragments of shell, bone, or even shark's teeth. They may not look particularly impressive, but these nodules, often dubbed the truffles of the ocean, are rich in highly sought-after precious metals like nickel, copper, cobalt, and manganese. The very same metals used in electric vehicles, wind turbines, and long-lasting batteries. Sweetman and his team have hypothesized that the minerals in polymetallic nodules are acting a bit like natural batteries, generating tiny electrical currents that can split water molecules into hydrogen and oxygen, even in complete darkness. If the latest phase of this research mission confirms the hypothesis to be correct, these nodules could be supporting the life and habitats found in the rich ecosystems of the deep sea. While the deep sea was once thought to be devoid of life, we know now that it is the largest habitable space on the planet and home to a dazzling array of life. In fact, in the nodule-rich Clarion-Clipperton Zone, scientists recently discovered more than 5,000 species entirely new to science. The same zone, however, is increasingly being targeted for deep-sea mining. As well as being rich in biodiversity, the Clarion-Clipperton Zone lies in international waters, and it has already been earmarked by 17 mining contractors. The argument for their interest in the deep seabed is that the energy transition is driving up demand for nickel, cobalt, and manganese. Some agencies project that demand will more than double over the next 2 decades. For some, deep-sea mining is viewed as a critical means of securing these metals. The Canadian mining firm, The Metals Company, has applied to the US government for a permit to begin deep-sea mining in the very same place where these dark oxygen experiments are taking place. The Metals Company also partly funded Sweetman's original research, which discovered dark oxygen. They have since sharply criticised his findings. Earlier this month, the Japanese government also launched a deep-sea mining test expedition to extract precious metals from the seafloor, some 6,000 metres below sea level. Interestingly, the Nippon Foundation, who are funding this research project, were crucial to the discovery of the nodules now being targeted by the Japanese government. In 2024, prior to Sweetman's declaration of dark oxygen, the Nippon Foundation had partnered with the University of Tokyo and made clear its plans to experiment with large-scale extraction of metallic nodules from the deep seabed by 2026 and 2027. The Foundation has since claimed to have placed a moratorium on this particular project. The organisation was also keen to stress its desire to balance conservation with deep-sea mining, 2 activities which are not often uttered in the same breath. So what implications could this mission have for the future of deep-sea mining? With the expedition setting out this April, we should have their findings by June, When asked about how its research might affect the future of deep-sea mining, the Nippon Foundation said its work intended to provide objective evidence about how the nodules function and their role in the deep-sea ecosystem. Mr. Mitsuyuki Uno, Executive Director of the Nippon Foundation, said,
"We don't want to be influenced by preconception or principle or position, but we want to obtain objective evidential data and then provide that to each country of this world. And so based on that data, if each country will be able to comprehensively make a decision and take action based on that, I think there is a meaning and significance to this research."
Countries like Japan, Brazil, Norway, China, and India have all been ramping up efforts to explore deep-sea mining areas that fall within their economic zone. And US President Donald Trump has pushed for the extraction of these nodules to start. It is hard to understate the enormous impact deep-sea mining could have on our ocean. Its equipment, the chemical discharge, and noise pollution could kill a huge array of marine life, from whales to the microscopic organisms that support the entire food chain. The loss of this deep-sea biodiversity might also impact the ocean's carbon cycle and reduce its ability to help mitigate global temperature rise. And when we asked about the environmental impact of deep-sea mining, Professor Sweetman said that if commercial mining goes ahead, there will be widespread impacts. He added that the nodules themselves are home to a variety of diverse fauna, but he positioned the research as informing rather than opposing mining.
As I said before, projects that are looking at the impact of deep sea mining, I don't think any of them are really trying to say, okay, we're going to find something to stop deep sea mining. That's not our intention. But what we want to do is to try to get as much information as we can, a variety of different areas, look at how important it is, look at how ecologically relevant it is, figure out what's causing it, so that if mining does go ahead, we can suggest practices that limit the damage as much as possible. Because if we don't, the damage will be big.
Despite the potential environmental importance of dark oxygen, Nippon's executive director seemed hopeful that the solution to deep-sea mining could be found in further scientific research.
But if we do find that dark oxygen exists, it does not mean that we have to stop deep sea mining altogether. Because let's say that if this project does able to confirm the dark oxygen existence in the deep sea zone, and it proves that it is going to play a major role in maintaining the ecosystem of the deep sea floor, still, I think the scientific research will be able to come up with new sustainable use or way of doing things as a result.
Professor Franz M. Geiger made a starker point about how little we currently know about the importance of dark oxygen.
I see us really standing at a similar point in time where the knowledge was at the level before we understood how DDT impacted the biosphere or how fluorocarbons impacted the ozone layer. We're about 10 to 15, maybe even 20 years before that. So we'll see what we find, but this is to me the analogy.
Global ocean governance remains in a critical state. While the landmark High Seas Treaty has officially entered into force, the International Seabed Authority has yet to rule on whether deep-sea mining should be allowed. And scientific expeditions are just now setting out to discover the environmental significance of dark oxygen. These ancient nodules containing precious metals might hold the key to the age-old question of how marine life is sustained on the deep sea. But with their geopolitical advantage growing, will countries exploit another under-researched finite resource in a bid to get to the top of the burgeoning green energy arms race? It is certainly a development to keep an eye on. If you would like to learn more about this story, or other stories related to deep-sea mining, head to the Oceanographic Newsroom. This has been the Ocean News Podcast. I've been Eva Cahill. Thank you for listening.